Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, welcome to this online class Math 45 Calculus 3. In this lecture video discusses all the topics in chapter 1 of Calculus 3 entitled, as you can see here, polynomial approximations, sequences, and infinite series. However, I am going to divide the topics into two parts. The first part, I will be discussing sequence up to root test, and then the second part is from power series up to binomial series. Okay, so without further delay, let's start lesson 1. So as you can see here, the title of our lesson is sequences. So before I am going to explain to you the definition, first let me remind you that this topic, the first topic entitled sequences, is very important in the whole chapter. Why? Because as you can see, if you don't understand the meaning of the sequence, then all would be meaningless. You will not be able to understand what is infinite series, what do we mean by polynomial approximation, so all of that. So meaning to say, if you don't understand it, please repeat it again and again and again until you comprehend the idea of what it means to be a sequence. Okay, so let's start. Okay, a sequence, it says here in definition 1, as you can see here, definition 1, a sequence or infinite sequence is a real valued function whose domain is the set of integers greater than or equal to some integer. And notice that some books they define it as a sequence is a real valued function whose domain is the set of positive integers, but I prefer to choose this definition because as you can see, there are in the next topic, when we talk about infinite sequence, they will start at n is equal to 1, or maybe n is equal to 2, 4, and so on and so forth. So that is why I write here it will start at some integer n naught. Notice also the sequence is a function and the domain is the set. Okay, so let's forget about this one, the domain and so on and so forth. Let's focus on the keyword here, which is the word function. So forget about real valued. If you understand the definition of a function, then later on it's very easy to understand what do we mean by real valued function. Okay, so as the keyword here is as you can see, a sequence is a function. It is a function. So what do we mean by a function? So as you can see here, I'm sorry, I will try to put a color red. Okay, so the keyword here is a function. So if you try to recall your algebra class, trigonometry class, or pre-calculus class, or basic calculus class, a function, so let's try to recall this. So recall this. Let's try color red. A function is a rule that assigns to uh, each element x small x in the domain one and only one element y, so one element sorry element y in the codomain. Okay, so our small y here and small x are notation for element, and the big X and the big Y is notation for a set. So mm, if you recall your algebra or trigonometry class, it says there that this is the meaning of a function. And as you can see here, it's not clear again. It is a rule that assigns. So what do we mean by that? Okay, so what we will do here is we will try I will try to explain to you in layman's term. Okay, there are, in order for you to understand the definition of a function, let's try to understand this by describing it or by visualizing it. So we are not talking here about sequence first. Let's try to understand the word function. There are four ways on how to describe or visualize a function. Okay, so if you remember, the first one is using diagram. I know you are familiar with this diagram or mappings. Sorry, mappings. Okay, so I know you have an idea now. Let's try to make a diagram with my, yes, I have an oblong now, a perfect oblong, that one. Oh, okay, again, that's, I'm sorry, please wait. Oi, what happened? I think I have to copy this one first. Make a copy and then paste, control paste, that one. Okay, then I'm going to drag here. I'm sorry, I wasn't able to make it perfect. Okay, this is a diagram. As you have noticed here, this is our, let's try another color, let's say blue. This is the set X and the set Y. Okay, and then we have a mapping here. Let's denote this as F. And if you have an object, let's say negative 3, 2, 1, 7, say 11 or 12, and then on the codomain I have A, C, Z, 5. Okay, that one, there are 4 elements. So when you say a diagram and when you say a function, it says that the word there is, it is a rule that assigns to each mean to say every element of the domain must be mapped to one and only. So as you can see, the keyword there is one and only one element. So means example we have 3 is mapped to Z, your 2 is mapped to C, your 1 is mapped to 5, your 7 is mapped to Z again, your 12 is mapped to letter C. So as you have noticed here, every element in the domain is mapped to one and only one. Okay, so if there is one up arrow for each object here, this means that it is a function. Okay, so what will happen if there's more than an arrow? If there's more arrows in here, this means that this is not a function anymore. Okay, so the other term that for that is a relation. So remember in your algebra and trigonometry class, we have, so you remember, if there is two or more mappings, more arrows here, this means that it is now called a relation. Okay, so then notice that the domain, this is the domain here, and the other one is, this is the codomain. Okay, for this example, the domain here, which is x, is uh, had an element negative 3, 2, 1, 7, and 12, whereas the codomain had the element a, c, z, and 5, and the range of this uh, function are those objects in the codomain that is map, that has an arrow, or meaning to say, notice here, only C, Z, and 5 are mapped to every element in the domain. So meaning to say A is not included. So A, letter A, or the object A is not part of the, range of this function. So please remember the domain, the please remember the how the function is visualized using diagrams and or mappings. The second one, if you remember, is through ordered pairs. Ordered pairs. Okay, so for example, this one, our notation here is f. For this example, our function is this. If we describe using ordered pairs, then as you can see, this will be, the elements are this one, negative 3z, 2c, and then 1, 5, 7z, and 12c. So as you can see here, if we describe the function using ordered pairs, this is it. Okay, then as you have noticed, when you look at your previous notebooks, as you can see here, no two ordered pairs have the same first component. So as you can see, the definition in your previous subject, no two first component, okay, are the same. So that is a function. Okay, the third one is using tables. So for example, if you have this one, uh, So this is our x and y. This example here, as you can see, we have negative 3z, 2c, 1, 5, 7z, and 12c. So if you are going to describe the function using tables or tabular description of a function, as you can see here in the upper part, no two first are no two object here are repeated. Okay, so that's what it means to be a function. The last one is, which is very important, is using equations. So there are, in your algebra and trigonometry class, uh, you will see that there are functions that we already discussed, like for example of these are the linear functions. Linear functions. Do you remember the quadratic functions? Uh, how about logarithmic functions? Natural logarithmic, trigonometric functions, trigonometric functions. There are a lot more exponential functions. Remember that, exponential functions, and uh, many other. Okay, so this is described by this notation: y is equal to f of x. And if you remember the vertical line test, the horizontal line test, the vertical line test, for if you want to determine if the given equation is a function or not, of course you have a graph. So as you can see here, uh, I've already discussed to you what it means to be a function. Okay, so for our notation, let's discuss it here. For our notation, for a function, notation, this is described as f of x, this one, f maps to y, where our small x here is maps to small y. Or you can write this one as, this is our f of x. Okay, so meaning to say, every element here, for example, this example here, our example, our negative 3 is mapped to z, uh, 2 is mapped to c, 1 is mapped to 5, 7 is mapped to z again, 12 is mapped to c. So this is a function because no two objects here in the domain are repeated. Okay, so let's go back now to our definition. It says here that a sequence, so let's try to explain this one. A sequence is a function, real valued function, meaning to say real valued is the domain must be the codomain must be real. So whose domain is the set of integers greater than or equal to some integer n not. So we will be, sorry, I had to erase this one and try to explain this. Okay, so our function whose domain is this one, set of integers up to n sub o plus n, which is maps to the set of real number. Why? This is because it is a real valued function. As you can see here, real valued function. It is a real valued function whose domain. But usually in your book, we take uh, usually uh, usually our n sub o is always equal to 1. So meaning to say, if it's equal to 1, then our function now will become 1, 2, 3, 4, and so on up to it maps to the set of real numbers. If our n naught is equal to 1, if n naught is equal to 0, then it will start from 0, 1, 2, 3 up to n. Or if it will start from 5, then we have 5, 6, 7, 8 up to n, and so on up to infinity. So meaning to say here is that the one here is mapped to our object in the codomain, which is we will be denoting it as a 1. Okay, and then when it is 2, we have a sub 2. When it is 3, we have a 3, and so on. You have n, we have a n. And this is our f of 1, and this is our f of 2, our notation before, f of 3, and so on, f of n. Okay, so what you will see here is that there's nothing much more pleasing when we study the domain of the sequence. The most important here is the, what do you call this one, the range of the sequence. Okay, so meaning to say, we will be focusing our study in the range of the sequence. Okay, and as you notice here, I'm going to explain again here that we will be studying all these elements of the range of the sequence E4 up to En. So this is now our sequence, and the shorthand notation for this, shorthand notation, sometimes in a shorthand notation, is we will be using this notation E sub n. N starts from 1 to infinity if starts from 1. If it starts from 0, then you replace this one by 0. If it starts from 2 or 3, then you replace this one, or you can use this notation, okay, without n is equal to 1 up to infinity. Okay, so I simplified all the details, the details about the idea of a sequence, and in this discussion, I will be giving you an example. Okay, so let's have an example. Let's say I have an example here. uh, Example this one. You are given a sequence. Sorry, you are given a sequence. You know this notation on already. This is the set of uh, sorry, I think this is the set of positive integers. Okay, or depends upon the book, defined by, let's say for example, f of n is equal to 3n minus 2. Okay, so let's try to list the elements of the sequence. By the way, a1 and a2 here, a1, a2, a3 are, these are the terms of the sequence, or elements of the, I'm sorry, this is the elements of the sequence. Okay, not the terms. The terms is used in the infinite series. Okay, so if you try to list the element of the sequence, notice that 1 is mapped to, say, f of 1. So what is f of 1? 3 times 1 minus 2, which is 1. We have 2. We have 3 times 2 minus 2, which is 3 times 2 is 6. We have 4, and so on. So these are the first 3 elements of the sequence. No, sorry. 3 times 3 minus 2, we have 9, 7, and so on and so forth. If you have n, we have f of n, which is 3n minus 2. So these are now the elements of the sequence. Tricolor blue, sorry, color blue. These are now the elements of the sequence. 1, 4, 7. I think we have a distance of 3, a difference of 3. So we have 1 plus 3. We have, I guess this is 10, and so on, up to 3n minus 2. Okay, this is an infinite sequence. So notice in the definition of the sequence, you cannot rearrange the elements. A1 must come first, followed by A2, and then followed by A3, A4, up to A5, up to AN. You cannot rearrange the sequence, meaning to say you will put 10 first, and then 4, and then 7. No, you have to arrange in increasing order. Okay, so please don't forget that. Or in shorthand notation, you can write this one as 3n minus 2, meaning to say when n is equal to 1, we have 1, and n is equal to 2, we have 4, and so on, because this is our an. Okay, so that's the first example. Let's have a second example. So let's try to name this one as example 1. So for example number 2, another example, we have, let's say, f maps to from the set of positive integers to real number r defined by uh, f of n 4 over n plus 1. So let's have a solution here. So R1 is mapped to f of 1, which is 4 over 1 plus 1, which is 2. For n is equal to 2, we have f of 2. 4 over 2 plus 1, which is 4 over 3. So when n is equal to 3, f of 3 is 4 over 3 plus 1, which is 1. Okay, and so on and so forth up to n, which is f of n 4 over n plus 1, and so on and so forth. This one, this one. So our sequence here is denoted as 2, 4 third, 1, so on and so forth up to 4 over n plus 1. Okay, you can write the first 5 elements of the sequence or first 4 elements of the sequence. Okay, this is, if you have the shorthand notation, this is 4 over n plus 1, and this is our an. Okay, so I think that's clear, no, very clear now. Okay, so for the second this one, for the second definition, we will be talking about the limit of the sequence. So as you can see, the domain is from the set of what do you call this one, integers greater than or equal to n naught, some integer n naught. As you can see, we have an infinite sequence, no, because it's, as you can see the dot here, dot. Okay, so that's an means it is an infinite sequence. So you are be finding the limit as n approaches to infinity. Okay, so the limit of the sequence is very similar to now for now I will be discussing definition number 2. Okay, so don't forget we are on definition number 2 now. The limit of the sequence is just very similar to the idea of the limit in your calculus 1 when you talk about, if you remember, about limits at infinity. Okay, so just recall your uh, calculus 1 uh, about limits at infinity. So this is the formal definition and limit of a limit of a sequence. This is not intuitive, but as you can see, they are very similar in calculus 1. A sequence an, because it is a function, is said to have a limit L if for every epsilon greater than 0 there exists a number n which is greater than 0. This number n here need not to be an integer. It could be a real number. It will be a real number. Okay, so such that the distance between the function and its limit is less than epsilon for every integer n, small n, greater than this real number here. And we write the notation as this one: limit of an as n approaches to infinity is equal to L. Okay, okay, so let's have an example here. Let's have an example for definition number 2. Let's try this space here. This is about limits. Uh, if you recall your limit, recall the topic in calculus 1, limits at infinity. So did you remember this theorem? If r is a positive integer, then we have 1. The limit of 1 over x to the r, as our r approaches to positive infinity, is equal to 0. And the same also for r approaches to negative infinity. It's also 0. So this is a topic in calculus 1 that you should recall. Okay, so let's have an example. Let's say, let's try the green one. uh, Example, evaluate uh, limit of 5n of the sequence 5n over 3n plus 2 as n approaches to positive infinity. Okay, so solution. Okay, first you have to copy the problem. By the way, if you replace your n with x just the same, the same method in study in approaching this problem. So we have here 5n, so you will multiply both sides by 1 over n. This is how you are going to attack this problem. And then multiply this one to the numerator. Here we have 5, and the denominator becomes 3 plus 2 over n. And notice that as n approaches to infinity, this will become 5. The limit of a constant is a constant, 0, and this is equal to, the answer is 5/3. Okay, so let's try to put a box here. Okay, so the limit of the sequence 5n over 3n plus 2 is 5/3 as n approaches to infinity. Okay, so before, how would you know that this, what do you call this one, how would you know that the limit is really 5 over 3? So if you recall your algebra or trigonometry class, you can graph this function, and then observe that as n approaches to infinity, then that will become the limit will 5 over 3. But let's try to graph this. Okay, so and the Cartesian plane. Let's try to, sorry, open the Desmos graphing a sequence, graphing sequence, sequences. You can try using Desmos. I think this one. Let's open the app, the website. Okay, so there is actually a difference between real function. I mean, when you say real function, the domain is real, but our sequence, the domain is, it is no, 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 no. When you say real function, it is the domain and the range are the same. But if you have a sequence, the domain is the set of, is a subset of a positive integer. Okay, so okay, this is an example of a sequence. The sequence a 1 over x. Okay, so you have, if you have 10 elements, as why, let's try to zoom this out. Why do we have a Desmos? I'm sorry, Desmos. Why do we have a dot here? As you have noticed, since our domain is the set of positive integers, remember that 1/2, 3/4 are not included in the domain. So this is the reason why you have a dot. Okay, so this when you try to answer a problem in sequence, and if you want to graph it, then this means that the graph will look like this. Okay, this is because between, as you have noticed, between 1 and 2, the point 1 up to 0.01 up to 0.999 is not included. Okay, same is true for 2 to 3, no, 2.01 up to 2.999 is not included, 2 and 1/2 is not included. So as you have noticed here, there is a gap between, let's say this is from 7 to 8, as you can see here, from 7, there is no point here, there is no dot here. This means that this is because we did not include these points between 7 and 8. The same is true for 5 and 6, for 6 and 7, and so on and so forth. Okay, so that is the reason why that is the reason why uh, there is a gap, or there is a gap between here. Okay, so for example, our example before, 5n over 3n plus 2. So if you replace this one as 5x, okay, 5n is 5x over 3x, 3, am I right, 3x plus 2 plus 2. Okay, what happened? Next, enter, can I enter that one? Okay, no, enter this one and enter this one. What happened? Where's the, I don't know what happened. Where's the, sorry, I think we have to get another uh, where's the other one? I think I have to recall in the history. uh, let's try to this one. I think this one. Okay, okay, just wait. Okay, so since we are waiting for the website to load, okay, it's here as you can see here. Okay, just trying to make this bigger. Okay, so let's try, for example, our example here. When where's that one? Where is, no, wala. No, we can't find. Okay, let's try. When n is equal to 1, let's try to uh, sorry, back. Let's try to use another. When n no, when n is equal to 1, we have this maps to 5 over 5 times 1, 5 over 5, and this is equal to 1. Okay, when n is equal to 2, this is 5 times 2. We have 10 over 3 times 2, 9. 3 times 2, 6, plus 2, 8. 10 over 8. Or this is divide to 5. I think let's try to use another 5, 4. When n is equal to 3, we have 3 times 5, 15. 3 times 3, 9, plus 2, 11. Okay, that one. So let's try to graph this one. When it is 1, then it is mapped to 1. Okay, 1. Sorry. When it is 2, as you can see, let's try to delete that one. When it is 2, it is equivalent to 5 over 4. 5 over 4. Okay, so when it is 3, what is 3? 15 over 11. 15 over 11. Okay, so as you can see here, to forget about these points here. Okay, these points here, as you can see, it is approaches to what is the limit? 5 over 3. Okay, which is the 5 over 3. What is the value of 5 over 3? So check your calculator. I guess that there will be a limit here, uh, which is equal to 5 over 3. So that's definition number 2. But if you try to solve to prove that the limit is really equal to 2 using the definition, so let's try to answer this one. So if you recall your uh, calculus again, calculus 1, let's prove this. Let's try to prove using definition. So meaning to say, we have to find a we have to find the big N. We have to find the big N by this one solving this one. Okay, so let's we have to get an epsilon, so let epsilon be greater than 0. Then let's try to solve an minus n. So as you can see, our limit is 5/3, so we have our function is 5n over 3n, sorry, 3n plus 2 minus 5 over 3. So let's try to simplify this, get the LCD. Our LCD is 3n plus 2, sorry, plus 2. So divide times, so we have 3 times 5n is 15, and minus 5 times 3n plus 2. Okay, let's move this up. Then if you further simplify this will become 3n plus 2. So we have 15n minus 15n minus 10. Am I right? So we have to add that one. This becomes 0. No, we have blue. So we have negative 10 over 3n plus 2. Okay, so notice that since our n are positive integers, then we can remove the absolute value. This is 3 times 3n plus 2. So let's try to erase this one in blue. Okay, so what should we do here? So this will become 10 over 3 times 3n plus 2 less than epsilon. So because if you look at the definition, this is less than epsilon. We are trying to solve this by separating epsilon and n. Okay, so cross multiply, we have 10 less than 3 epsilon 3n plus 2. So divide both sides by 3 epsilon, cancel. You can cancel out that one because our epsilon is greater than 0, so epsilon is not equal to 0. So we have 10 over 3 epsilon less than 3n plus 2. So you can transfer on the other side our 2, and then try to combine Okay, this is 10 minus 3 epsilon times 2 is 6 epsilon 3n. So again, you can multiply both sides by 1/3, multiply both sides by 1/3, then you can cancel out. So this will become, let's change this to this one, and notice the sign. This is 10 minus 6 epsilon over 9 epsilon. So therefore, our big N is 10 minus 6 epsilon over 9 epsilon. Okay, why? As you have noticed, notice this one, that it must be n, small n must be greater than this one. So let's recall our definition. Where is our definition? Yeah, this one, this. Okay, so meaning to say, uh, if your n is this one, then the absolute value of the sequence a sub n minus l is less than epsilon. So in particular, in particular, if you have epsilon, which is, let's say, 0.1, then our n is what? Let's try to solve that one. For example, we have 10 minus 6 times 0.1, and then 9 times 0.1. So what is the value of our, here's my calculator. This is my calculator. uh, 10 is my calculator. 10 minus 6 times 0.1 over 9 times 0.1. So our answer is 10.44. So this is 10.44. So meaning to say, we can choose our small n to be 11 or 12, so on. Meaning to say, when n is equal to 11 or 12, then the absolute value of the sequence a sub n minus l is less than epsilon. Okay. Hello everyone, I'm sorry I have to insert this video in the whole video tutorial, because I have some minor corrections. Actually, there are two minor corrections that I have to point out. uh, for example, this one, I write it as a sub 5, so I guess this is correct. This is a sub n. Okay, so I have to erase this one, and then I will write as a sub n. Okay, that's only the minor correction. And also, as you can see here in the definition of, in the second definition, I did not elaborate this as much. When I try to prove the limit of an example, I did not write it in a graceful manner, but what I just did last uh, last night is that uh, I only uh, try to find the value of the big N in terms of the epsilon. Okay, so that's only the sketch of proof. But if you want a thesis like proof, then you should have to refer some books, maybe Lighthold or uh, Larson. You can look at the reference in this at the end of this video. Okay, but anyway, I have to elaborate that more by showing that uh, this one, uh, also this one, this is not R, this is not R, this one, this is not R, but this is X, as X approaches to positive infinity, and this is also X. Okay, I have to correct uh, this one by uh, deleting this or erasing this one, also this. Okay, it should be as X approaches to positive infinity. Okay, what I will show you is to show this example. If the limit, why is it that the limit is 5 over 3 by using the what they call this one, the definition. Okay, so as you can see, if this is the, if you look at the graph of the sequence 5n over 3n plus 2, for example, if you will go to the, what do you call this one, Dismos graphing calculator. If you look at the Dismos graphing calculator, you will see that why is it that the, what do you call this one, the limit of this function is 5 over 3 by using the definition. I prove it here, and then we saw that our big N is 10 minus 6 epsilon over 9 epsilon, and in particular if your epsilon is 0.1, you have your N will start you start at small n, which is equal to 11. Now this is the starting point. If epsilon is 0.1, what if epsilon is 0.2? Then you have another value of n. So what does it mean? Okay, what does it mean? So let's try to analyze that using a graph. No? So using a graph, so if you have this one, notice that our function is a sequence is 5n over 3n plus 2, but we have to replace it by x, and then imagine that there's a, the graph is only a dot. Okay, it's just a dot. Okay, so 5x over 3x plus 2. So let's try to graph that. 5x over 3x plus 2. Okay, so this is the graph of the, equation, the function. Okay, and notice that the limit is 5 over 3. The limit is 5 over 3. So as you can see here, so let's try to show if the limit is really 5 over 3 as n approaches to infinity. So let's try, I'm sorry, is equal to 5 over 3. Okay, so enter. Let's hit the function enter, and then as you notice here in the graph, you have 1 2 3 as n approaches to infinity. Here up to, as you can see here, the graph never touches to the line y is equal to 5 over 3. So it's clearly, if you extend that one, it never touches. Even if you expand, that, if you expand, as you can see, it never touches. to the line y is equal to 5 over 3. So that is why the reason is the limit is 5 over 3. So what does it mean by choosing an epsilon which is zero point 0.1, and the value of n is, why is it that is it 11? Okay, so I will try to let's try to analyze that one. Notice that illustration, further further uh, let's let's try another color, let's say red. Okay, further explanation. Okay, notice that this is familiar in definition number 2. Okay, in your algebra and trigonometry class, this means that this is equal, if you recall it in algebra class, this we know that absolute value of x which is less than to a number a, this is equivalent to negative a less than x less than a. So I know that you remember this. We will apply this property of the absolute value to this inequality. So our x here is a sub n minus l, and our a here is epsilon. So this is negative epsilon less than a sub n minus l less than epsilon. Okay, but this is, if we simplify this, this can be expressed as l minus epsilon less than a sub n less than epsilon. No, less than L plus epsilon. Okay, so since our L note, let's have a note here that our L is 5/3 and our epsilon is 0.1, our big N is 10.44, and our small n is, it will start from 11. Okay, uh, so if you substitute all these values, example, 5/3 is 1.667. So let's try to truncate that one. 1.667 minus 0.1 less than a sub n less than 1.667 plus 0.1. This is equal to, on the right side we have 1.767, and on the left side this is 1.567. Okay, so if you will try to make a table, okay, so this is your n and this is your a sub n. Okay, sample that one. Okay, this is 1 2 3 4 5. So this is 1. Then if you substitute our a sub n, note that our a sub n, where should I put this one, a sub n is 5n over 3n plus 2. Notice that our n, if you substitute n is equal to 1 to this equation of the sequence, we have 5 times 1 over 3 times 1 plus 2. This is 1. If n is equal to 2, you will have 1 point, I already what do you call this one, solve this. This is 5 over 4, or this is 1.25. If n is equal to 3, this is 1.363. If 4 is 1.43, and so on and so forth. As you have noticed, if your epsilon is 0.01 and your this means that your big N is 10.44, notice that when n is equal to 1, 2, 3, the values, the value of a sub n will not satisfy this inequality. Okay, so we know that 1.5, we know that this one 1.567 is not less than 1, but true in the other side. Okay, so meaning to say, for all values of n from 1 up to 10. Okay, example, if you have here, if you have 10 here, then the value is 1.5625. Again, as you have noticed, 1.625 is not greater than 1.567, but less than 1.767. Okay, if your n is 11, then the value of a sub n is 1.571. Okay, 1.571. And as you have noticed, if our n is 11, then this statement here is true onwards for all values of n greater than or equal to 11. Okay, for epsilon is for epsilon, which is equal to 0.1. Okay, so what does it mean if you look at the graph? Okay, if you look at the graph, so get this value here, 1.567 and 1.767. So if you try to substitute that 1.567, so if your y is y is equal to 1.567. Okay, that's the green one. And also enter, if your another is 1.767, y is equal to 7 6 no 1 point back 1.767. Okay, enter, hit the enter. And as you have noticed here, forget the blue one, no, the blue one, but consider on the green one, this one, green one, and the violet one, that line. As you have noticed, when n is equal to 1 to 1 2 3 4, it is outside of the tube. Okay, consider this one here, that one, this is a tube. Okay, then these points here, these points here are outside of the tube when epsilon is 0.1. However, if you go up to, let's say, 10, n is equal to 10, let's zoom in. If you zoom in, again, the value of uh, n, which is equal to 10, is also outside. Notice, it is outside of the tube. The tube from this one, blue one, and the green one, it's outside. But if it is, what do you call this one? If you look at 11, this one, 11, okay? Look at 11, this is 11. Notice that it is inside the tube, inside the top. For all n up to, can you see the what they call this one, this red color, red here? This is the graph of the sequence
5n over 3n plus 2. Okay? It is inside all throughout up to infinity. That is the meaning of the this one. The distance between the function values and the difference between the function values and its limit is less than epsilon. That's the meaning of it. Okay? So, uh, that's the reason. If you look at the definition too, that is the mainly the explanation. Why is it that if the limit is correct, then you don't have a problem in the graph. But if your limit is not correct, if the limit does not exist, then you cannot find the value, big N. It says there exists a number N, big N, a number N which is greater than 0, which is not necessarily a positive a positive integer, but it is a positive number. Okay, so that's I missed in the previous videos, so that's why I have to insert this. So be careful that you have to analyze this all throughout, because this you are a mathematics student. Okay, you are a BS math student. If you are a physics student, you are a chemistry student, or engineering student, then you have to analyze these things. Okay, so I hope you understand this. If you did not, then repeat it again until you understand. Then do not focus on the on this in this example, but you have to make another example. Try it to with another epsilon or another example. uh, then you will find that the definition of the limit will works if, yeah, if all will takes in place, of course. Okay, so I hope you enjoy learning. Thank you so much for watching this. I'm going to insert this one to our our series of videos. Okay, God bless you everyone. Okay, God bless. So that's definition number 2. Okay, for definition number 3, if a sequence a sub n has a limit, the sequence is said to be convergent, and we say that a sub n converges to that limit. Otherwise, it is divergent. So as you can see in the definition, if the sequence has a limit, then that sequence is said to be convergent. But if it doesn't have a limit, then the sequence is divergent. Okay, that's very easy. It follows from the definition number 2. Okay, so for our second lesson, that's all for today. For this lesson 1. For the second lesson, we will be talking about monotonic and monotonic and bounded sequences. But before that, if you remember this theorem, this is true also in your calculus 1 subject. The limit of a constant is a constant sequence is a constant. The limit of a constant times the sequence is, you can factor out the constant from that sequence. The limit of a sum and difference, you can distribute. As you can see here, you can distribute. The limit of a product is the same. The limit of a quotient is the same as in calculus 1, provided that the denominator must not be equal to 0. So for example, let's have an example. Example number 1.
If you have the limit of a constant, let's say if you have a sequence which is this one, okay, so meaning to say, if you will try to explain this is our sequence. Example, it starts from n is equal to 1, so meaning to say 1 is mapped to 5, 2 is mapped to 5, 3 is mapped to 5, so this is our a1, a2, a3, and so on, and up to 5 decisions. So the answer is 5. Sorry. So meaning to say, this sequence is denoted as 5, 5, 5, 5, and so on. 5. Sorry. That one. Okay. So the limit of this sequence, the limit of the sequence is as n approaches to infinity. I'm sorry, this is, I think this is, no, let's erase this one. The limit of is 5. Another example, I'm sorry, I think this notation is, I see, yes, yes, this is correct. Our an is 5. Okay, so for the second theorem, example, if you have the limit of let's say 6 n over n plus 1, as n approaches to infinity, you can factor out 6, okay, over n plus 1 as n approaches to infinity. So we can multiply by 1 over n, so this is 1 plus 1 over 1 over n, sorry, 1 over n. 6 limit, no, not limit, can evaluate now. This is 1 over 1 plus 0, so the answer is 6. Okay, and same is true for number 3, number 4, and so on and so forth. So for example, we have this one, limit of 3n minus 2 as n approaches to infinity. You can distribute the limit minus limit of the constant as n approaches to, notice that this is the answer, this one is 2, this is 2, but this one is infinity, so this is, answer is infinity. Infinity minus a number is infinity. Okay, so you will have an answer which is infinity, or maybe it's not, does not exist, doesn't you don't have an answer, does not exist in limits at infinity topic. Okay, so that's how it works if you have if you will use this theorem. This is the same as your
your calculus 1 subject. So again, don't forget, our next topic will be discussing about monotonic and bounded sequences. Okay, God bless everyone. Let's start. So before we proceed to our lesson number 2, which is monotonic and bounded sequences, let me have some examples further examples in lesson number 1. Okay, so sorry let's create a new whiteboard. So let's have further examples in lesson number 1. So example uh, examples in lesson 1. So for the following problems, determine if the sequence is convergent or divergent. So means say we have to find the limit. So for problem number 1, we have 3n squared plus 1 over 2n squared minus n. So let's have a solution. So first is we will evaluate the limit. Copy the problem first as n approaches to infinity. By the way, before I forget, again, I made a mistake in the first lesson since it's already very lengthy uh, recording. So let me remind you that I made a mistake about the theorem at limits at infinity. So just like this theorem, uh, you remember it. Okay, this theorem about limits at infinity. If r is a positive integer, then number 1, the limit of 1 over x to the r. As before, I write it as r approaches to positive infinity, but I made a mistake. I forgot also this is as x approaches to positive infinity. This is 0, and the same is true for number 2, 1 over x to the r if our x approaches to negative infinity. It's also 0. Anyway, that's I know you are familiar with it. So let's continue solving this. 2n squared minus n. So we have to multiply by 1 over n squared as n approaches to positive infinity. And this will become 3 plus 1 over n squared. 2, the denominator is 2 minus 1 over n. As n approaches to infinity, am I right? Okay. So this will become Okay, see, we can evaluate now the limit. Let's go back. Okay, this is 3 plus 0 over 2 minus 0, and this is 3 halves. Okay, 3 halves. And this one 3 halves. Sorry, 3 halves. If you will try to graph it in a real line, not in a sequence, so you replace this as your x, replace it as x. Okay, your n, replace it as x. So let's try to graph this in Dismos. We have 3, sorry, shift, we have 3x squared, sorry, x squared, oops, shift, oh, what happened, sorry, this one, 3 3x squared, what happened to this mess, adds the other way, I think I will do this one, 3x squared plus 1 plus 1, sorry, that one, divided by over 2x squared minus x, 2 2x squared, 2x squared minus x. So that's the graph. As you have noticed, here, there should be a dot. Since we start with 1, there must be a dot here, that also. And as you have noticed, it really approaches to what is our limit, 3 and 3 over 2, meaning to say this is 1 and 1 half, 1 and 1 half, so 1 and 1 half. So clearly there is a, you notice here, a graph here, as x approaches to infinity, as n approaches to infinity. So we replace our n to be our real number, and it's just the same. All you have to do is to not include the points here between 1 and 2. Okay, there must be a dot here, and so on and so forth. Okay, there must be a dot there. So as you have noticed, it approaches to 3 halves, or 1 and 1 half. So it verifies our result. Okay, so this is correct for number 1. This is correct. For number 2, let's try number 2. We have e to the n over n. So solution, get the limit as n approaches to infinity. So what is the value of this problem as n approaches to infinity? So
notice that this problem is of the form uh, positive infinity over positive infinity. So meaning to say, we can apply the, you remember your calculus 2, you can apply the L'Hopital's rule. Okay, so by LHR, so this is the derivative with respect to n is e to the n over 1 as n approaches to infinity. So this is by LHR. Oops, sorry. But uh, the limit of e to the x is e to the x. Okay, so simplify as n approaches to infinity, and as you have noticed, we have positive infinity. Okay, so if you try to graph this uh, problem, replace n by x. Where's the exponential? Let's try exponential, this one, of hmm, sorry, x over divided by x. I think I have to replace the color to, red. Okay, so if you have noticed the red one, as x approaches to infinity, this, I think this is clear. As x approaches as your n approaches infinity, 1 2 3 4 5 up to infinity, the graph, as you have noticed here, this one gets bigger and bigger. So the answer is positive infinity. So that verifies our result. For our third problem, oh sorry, back. Third problem. Our third problem is this one. What if you are given n squared plus 1, 2n plus 1? So this is our sequence. Solution. Um, Limit, copy the problem first. N squared plus 1, 2n plus 1 as n approaches to positive infinity. Copy the problem first. N plus 1 as n approaches to infinity. So what should we multiply both sides of this equation? So I guess we are going to multiply 1 over square root of n squared. 1 over square root of n squared, so that we can combine this one. Okay, so if you try to distribute, limit of this will become n squared plus 1 over n squared. In the denominator, as you have noticed, this is 1 over n, since our n approaches to positive infinity. So as n approaches to positive infinity, so this is 2 plus 1 over n. So further simplify the result, this will become uh, square root of 1 plus 1 over n squared, 2 plus 1 over n as n approaches to infinity, and this will become, the limit is, you can evaluate now. From here is simplify, so this is square root of 1 plus 0, 2 plus 0, and this is 1 half. So our answer is 1 half. Okay, so let's verify this problem again in a graph. Replace n by x. Okay, so it must be square root. Where is square root of, first that one, x squared plus 1, square root of x squared plus 1 divided by 2x plus 1, 2x plus 1, and the color, the graph is the green one. Where's the green one? So let's try to zoom. So this is 1 here, so 1 half is here, and as you have noticed, as n approaches to infinity, the limit is clearly 1 half. Okay, so that's verifies our result. So how about number 4, the last problem, number 4, last problem. What is the limit of this sequence over to the end? So solution. So again, copy the problem first. Okay, this is 1 plus 3 over n to the n as n approaches to infinity. So how are we going to solve this? First is you have to I guess I'm going to give a hint. This is in calculus 2. Okay, this is your assignment. I will not solve this one. Okay, so I'm sorry, I forgot. Okay, so that's all. Thank you so much for listening. Now we can proceed to lesson number 2, which is all about monotonic and bounded sequences. Hi everyone.
Take me to Neverland.
For our second lesson, which is entitled monotonic and bounded sequences, let me remind you that you have to familiar yourselves about what I told you before in lesson number 1 about the sequence. You have to really try to understand our first topic. So since you are, I assume that you are familiar now the idea of a sequence, so let's proceed to lesson number 2. Okay, definition 1. This is all about increasing and decreasing sequence. A sequence a sub n is said to be increasing if this condition
satisfies for all n. Otherwise, the sequence is called decreasing. Okay, so before we discuss what is monotonic, let me give you a brief, a simple explanation of about increasing and decreasing function. If you graph the function in the graphing calculator or in Desmos, as you can see, as if your n is, if your example, if this one, this blue one, notice that as this one, as n approaches to positive infinity, 1 2 3 4, clearly the graph is decreasing. Okay, decreasing, so meaning to say this function is decreasing. 3n squared plus 1 over 2x squared minus x. How about the red one? This is an example of a sequence which is an increasing sequence. So you have noticed here, as when n is equal to 1, we have a dot here. When n is equal to 2, we have a dot here. N is equal to 3, a dot here, and so on, 4, and so on and so forth. So as you have noticed, it is increasing. So that's basically the definition comes. How about this function, the green one? Do not include this one, this graph here, because our sequence starts from 0 or 1 or 2 and so on and so forth. Okay, so for all n, remember that for all n, as n approaches to infinity, and as you can see, approaches to the limit, which is 1/2, just like before, our answers before. So this is example of decreasing function sequence. Okay, so as an example, very simple example, we have, how about this one? Where's my pen? So example, if you have this sequence, 4 over n plus 1. Oops. Okay, so as you can see, if we graph this one using this mouse again, 4 over n plus 1, 4 divided by n, x plus 1, x plus 1, the violet. Okay, as you can see, it is decreasing. Okay, so we expect that it is decreasing, so meaning to say, notice the definition of increasing function. So this one I'm going to, no, sorry, back. Okay, okay, this is for increasing, but how about if decreasing? So it's reverse. Okay, this is the, this is for decreasing. Okay, so since it is decreasing based on the graph, the violet one, so let's try to solve this. Okay, solution, we have an, we don't know, but in the graph we know that it is decreasing, so we don't know. This one, and plug in. So this is our an, this is our an, this is our en. En is 4 over n plus 1. So this is 4 over n plus 1 question mark. So remember that if we replace n by n plus 1, we have 4 over n plus 1 plus 1. Okay, and then cross multiply, we have
simplify first. N plus 1, 4 over n plus 2. So cross multiply, do 1, cross multiply, so we have 4, sorry, 4 n plus 2, question mark 4 n plus 1. So this is 4n plus 8, 4n plus 4. So as you have noticed, we can cancel out this one. We have 8 question mark 4, and clearly, oops, back. Sorry. This is 8 question mark 4, and clearly 8 is 8 is 8 is greater than 4. Oops, sorry. Okay, so this is therefore an is greater than an plus 1. Therefore the sequence 4 over n plus 1 is decreasing. Okay, oops, okay. So the function 4 over n plus 1 is a example of a decreasing function. So what do we mean by a monotonic sequence? It says here, if a function is increasing or decreasing, so remember the conjunction here, or, so either, so if it is increasing, either increasing or decreasing, then it is monotonic. So meaning to say, this example for the sequence 4 over n plus 1 is a monotonic. Therefore 4 over n plus 1 is a monotonic sequence, since by definition, if the function is increasing or decreasing, then it is monotonic. Okay, so number 2, definition number 2, definition about lower bound and upper bound. This is very easy to understand. The number c is called a lower bound of the sequence an if all of its term is this number here. You have to pick this number is less than or equal to every elements of the sequence for all positive integer n. And the number d is called the upper bound, sorry, of the sequence if it is bounded above. Now, this number d is greater than all the elements of the sequence for all positive integers n. So for example, this one, the sequence, as you can see, so our first element is 1, so 2, and then 4 divided by 2. How about 2 is 3/4? If 3, 1, 1, 2, 3, 4, 4 over 5. Am I right? Yes, 1, 4. If 6, if 1, 2, 3, 4, 5, 4 over 6. 4 over 6 is 2/3, and so on. So forth. This is 4 over n plus 1.
And as you can see, uh, this sequence has a limit and it is decreasing. The limit of this sequence is 1/2. Am I right? 1/2. Let's look at the graph if I remember it correctly. 1 2 3. Okay, is it 1/2? Yes. Okay, 1/2 or 0? Is it 0? I'm sorry. Did we solve this problem before? Where is that? Where's that? Where's that? Anyway, I forgot. So let's try to solve it. Uh, what is the limit? The limit of this function as n approaches to infinity. So we have 4 limit of 1 over n plus 1. So this is 0, I guess. Okay, 0. So as you have noticed, if you look at the graph, it approaches to 0 as n approaches to infinity. Okay, I'm sorry, I mistaken before. I thought it was the green one, but I think it is the violet one. That's why I mistaken. Okay, so the limit is 0. So it is decreasing and the limit is 0. So meaning to say, for this sequence, this the lower bound is sees here it says here that the lower bound is a number c. It could be less than or equal to the elements, so it could be 0, it could be -1 or -2, and so on and so forth. Okay, but the upper bound is here. As you can see, you can have 2, 3, 4, and so on and so forth. Okay, so there can be many upper bound or lower bounds. Okay, you can choose any number. If it is lower bound, it must be less than all the elements. If it is upper bound, then greater than or equal. Okay, our lesson number for our definition number 3, if a is
is a lower bound of a sequence, and if A has the property that for every lower bound C of the sequence this inequality is true, then A is called the greatest lower bound, and similarly the upper bound is defined as that. So meaning to say, if uh, example this one, these are A's, our A's, these are the lower bounds, 0, -1, -2, and so -3 could be our lower bound. It says here if that's our A, and if A has the property that every lower bound C, okay, so you can choose A or C here to be this one, but what is the exact inequality here is that this will follow. It must be, I'm sorry, but this is less than or equal, and also this one less than or equal. Okay, so when you say there are many lower bounds, but the greatest of all those lower bounds is what we call the greatest lower bound, then that A will be our greatest lower bound. So for example, this one, the greatest of this lower bound is this one. Our greatest is this one, 0. So this is our greatest lower bound, or GLB. Okay, because if this is our C, there are many C's here, this is the greatest of all the lower bounds. Similarly, for the upper bound, we have, okay, for the upper bound, there are many upper bounds, but the least of those upper bounds is what we call the least upper bound. So for example, this one, these are our upper bound, but the least is 2, this one. So this is our least upper bound. Okay, so notice that uh, the upper bound and lower bound could be an element of the set, but for this example, the lower bound 0 is not an element of this set. Okay, another example, uh, 0 is a greatest lower bound of this set, of this sequence 4 over n plus 1. Okay, okay, that's the meaning of the lower bound and the upper bound. So another example, if you have, how about our example before, another example, how about the sequence 5n over 3n plus 2. The elements of this sequence are the following. So 5, 1, so this is 1. First element is 1. 2, 10. So 10 over, so 10 over 3 times 2, 6, plus 2, 8. So this is 5 over 4. Okay, when 3, this is 5 over 5. 3, we have 15 over 17. 4, 20.
So 4, 12, 14. No, no, no. So sorry, this is 3. 3 times 1, 2, 3. 5, 3 times 2, 6, 7, 8. So this is 8. Sorry. So 4 times 3, 12. No. Sorry again. Uh, this is 3, 3 times 3, 9, 11. If 4, 12, 14. 14, so divided by 2, we have 7, 10 over 7, and so on. 5n over 3n plus 2. So what is the limit of this? We know that the limit is 5/3. Okay. Let's erase this one. The limit is 5/3. Okay. So what is the example of a lower bound? So which is bigger, 5/3 or 1? So 5 divided by 3 is 1.6. So what is the graph of this function? Let's try to graph this. 5 and 5x. 5, sorry, 5x divided by 3x plus 2. 3x plus 2. Okay. So we have the black one. So the lower bound is this one. It could be 1, 0, or 1/2, 1/4, 3/4, 0, -1, -2. So that is the lower bound. The upper bound are could be 5/3, uh, greater than 5/3. We have 2, 3, 4, and so on. But what is our greatest lower bound? So the greatest would be this one. Greatest lower bound. And this is our least. Will be our least upper bound. LUB. Okay. Okay, let's go back to definition number 4. A sequence AN is said to be bounded if uh, it has an upper bound and a lower bound. So as you can see here, these two examples is an example of a bounded sequence. Okay, this is a bounded sequence because it has an upper bound and a lower bound. Look at the definition. It doesn't mean that it says greatest lower bound or a least upper bound, but it says it has an upper bound and a lower bound. So if the sequence has an upper bound or a lower bound, then that sequence is bounded. So this example, 4 over sequence 4 over n plus 1, and okay, below the sequence 5n over 3n plus 2
is an example of a sequence which is a bounded sequence. Okay, let's have this theorem. Theorem, the axiom of completeness. This is a very familiar theorem in mathematics. Every set of real numbers which has a lower bound has a greatest lower bound. So if the sequence has a lower bound, then automatically the sequence has a greatest lower bound. Also, if it has an upper bound, then the sequence has a least upper bound. So that's what it said by the theorem, the axiom of completeness. For this theorem, a bounded monotonic sequence is convergent. So what does it mean? So meaning to say, when you say monotonic, it is increasing or decreasing since it is bounded. So it has an upper bound or a lower bound. So meaning to say, if that sequence is if the sequence is monotonic and at the same time is bounded, then it is convergent, meaning it has a limit. And for this theorem, third theorem, if you are given a sequence which is increasing, and suppose that this is an upper bound, the sequence, then the sequence is convergent. Of course, since it is increasing, then the upper bound, it will converge to it means to say that the limit must be less than the upper bound of the sequence. That is very obvious observation. The same is true for a decreasing sequence and for a lower bound sequence which will be denoted by C, and this one will reverse, okay, or the other one. For the last theorem, we have convergent monotonic sequence is bounded. So what does it mean? If the sequence is convergent and monotonic, meaning it is either increasing or decreasing, then it is bounded. All you have to do is to get an example of this. Try to explain, try to get an example to illustrate this theorem. Okay, so anything here is more significant, so just try some exercises in other books, calculus books that I've uh, given to you in the Google Classroom. Try to download that book or try to find other calculus book and then try to have an example to illustrate this theorem. Okay, for our next lesson, which is lesson number 3, it will be discussed in the next video. This is entitled Infinite Series of Constant Term. So remember that this lesson requires the idea of a sequence, which is very important, as I've said in the first uh, lesson. Okay.
That